1907, 2 years after the miracle year, Einstein had been asked to write a review article on the special theory of relativity for a science yearbook. It was really designed not for the general public necessarily, but for other scientists, just summarizing some of the key results of previous years. And he wrote later, reminisced later, that he had what he called the happiest thought or most fortunate thought of his life. In fact, here's how he described the situation. He had been bothered, as he thought more about the special theory of relativity, he was bothered by a couple things. And one thing was there's only constant velocity of motion, and therefore it wasn't general enough, and also didn't take into account any gravitational effects. So he had been mulling those things over. And later he reminisced that I was sitting in a chair in the patent office in Bern, Switzerland, when all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. And he says this revelation startled him. And as he thought more about it over the next 8 years, the end result was the development of his general theory of relativity. So even though in one sense it's beyond the course, we want to get at least a little insight into what that is all about and see actually in a couple instances, well, one instance at least, the one we're going to talk about in this video, it gives us a result that is similar to the special theory of relativity, but different in a couple of key respects, and that is a time dilation effect due to gravity. So he talked about that if a person, as he says, if a person falls freely, he will not feel his own weight. And so the classic example of doing that, and Einstein himself used this, would be in an elevator. Okay, so let's imagine that here's just it's a thought experiment, sort of an elevator out there in the middle of space. If it's falling freely, or even just a real elevator, if you cut the cable and there are no other safety mechanisms, as you fall freely, you will not feel your weight. If you drop a ball at that point, it will just stay there because you're all falling down toward the center of the Earth or down toward the surface of the Earth. So it'll be like gravity doesn't exist anymore. And Einstein started analyzing that situation a little bit more and noted also that if you, say for your elevator again, you attach a cable to it, right, and maybe there's a crane or something, again out in the middle of space, so somewhat fanciful here, but the idea is you have something where now you can lift the elevator up. In fact, you can accelerate it in an upward direction at some acceleration A. Again, just like we would do in a real elevator, as the elevator goes up, you feel that momentary push downward. You feel heavier. Okay, it's like gravity has actually increased. And so an acceleration upwards, if you're in the elevator, is therefore equivalent to a gravitational field. And this was essentially Einstein's happiest thought, and it came to be known as the equivalence principle. The equivalence principle, that essentially a gravitational field is equivalent to an accelerated frame of reference. Okay? That this person inside here, if they're walled off from everything, they could be in the most space for all they know. If the crane or the elevator or whatever, the cable pulls up on them at an acceleration that's equivalent to the acceleration due to gravity, then it feels like gravity to them. They couldn't tell whether they were in the elevator just on the surface of the Earth, feeling gravity pulling them down, or they're actually out in the middle of space and some imaginary crane is actually pulling them at an acceleration such that they press down into the floor, as it were, and you feel that normal gravitational pull. So that's the equivalence principle. Gravitational field is equivalent to an accelerated frame of reference. And so you see that opened up some things for Einstein because he was interested in going beyond the special theory of relativity, which is only constant velocity, inertial frames of reference. And here was something that enabled him to perhaps, if he pursued this, to bring in accelerated frames of reference and also tie it into gravity as well. And so again, over the next 8 years, in a number of stops and starts and dead ends and so on and so forth, plus he was working on other things along the way, he was able to come up with this general theory of relativity. And the key thing here for analysis is that what the equivalence principle enables you to do is if you do an analysis involving acceleration, then the conclusions from that analysis also apply to a gravitational field, a situation where you just have a gravitational field occurring. And we want to do 2 examples of that. In this video, we're going to do a time dilation example. In the next video, we'll do the bending of light example. And so let's imagine a situation like this. So we're going to have an elevator here. And we'll have our 2 observers, or really 2 clocks. And so we'll put a clock at the top of the elevator, clock U for upper, and down here we'll have clock L for lower. And these clocks emit little pulses of light. So here's one, and we'll get some nice red pulses of light coming up here in that direction. And then up here, another little laser and pulses of light going down. And we'll have a detector here and there. Okay? And so the clock, each clock, and these are synchronized clocks, the identical clocks, and they emit these little pulses of light. That maybe they emit 10 pulses of light per 1 tick of each clock. Okay? Now another factor here is that we're going to assume any velocities involved are much less than the speed of light. So this example will have nothing at all to do with the special theory of relativity. We'll assume the velocities are low enough that we can ignore all relativistic effects, if they're very, very small compared to anything else going on here. So we've got the clock, so that means that the 2 clocks are in sync with each other. Right? We don't have to worry about leading clock's lag and all that, because any velocities involved are much less than c. And we're going to now put this into acceleration in an upward direction. So we're going to accelerate it in upward direction, but again, at very, very small velocities, just sort of ordinary everyday velocities, so we can ignore any special relativistic effects there. And so let's think about what happens then to, say, clock L down here, the observer at clock L. They will be observing these pulses of light coming down to their detector here. And meanwhile, their pulses go up to the detector for clock U. But because as these pulses are emitted here, of course, they're traveling along now. But while they're traveling, the elevator moves up slightly. It's accelerated up a little bit here, such that these, let's say, there are, again, 10 pulses per tick of each clock. Okay, so clock L detector, though, because it's accelerated upward a little bit while these pulses are in motion, will collect more pulses per tick of its clock. It'll collect more of these pulses coming down because it's sort of moving up a little bit and sweeping through them a little bit faster because of the acceleration involved here. And so maybe instead of receiving 10 pulses, which it normally would do per tick of its clock, it receives 12 of these pulses of light coming down from the upper clock. So let's write that down. For clock L here, let's say it receives 12 pulses during 1 tick. 1 tick of its clock. Okay? So it receives 12 pulses coming down, whereas normally it would receive only 10. So what does that tell us then? It tells us that this clock, therefore, is running slower than this clock, okay? Because it's receiving 12 pulses during 1 tick. Well, they're both synchronized to do 10 pulses per tick, but now it's looking at the upper clock and it's getting 12 pulses per tick. So another way to look at it is the upper clock is running faster than it is. It's only doing 10 pulses. Well, it looks like the upper clock is doing 12 pulses in 1 tick. Therefore, the upper clock is running faster. You can also look at it the other way around if you want to do the perspective of the upper clock. It's accelerating, but it's accelerating away from the pulses coming up from the lower clock. And so as it gathers in those pulses at the detector, instead of maybe seeing 10 pulses coming in during 1 tick of its clock, 10 pulses from the lower clock, maybe it only receives 8 pulses during that 1 tick. So it's in terms of its clock, it's saying, oh, hey, I'm sending out 10 pulses per tick, everything's fine, but I'm only receiving 8 pulses per one of my ticks from clock L, and therefore it looks like the lower clock is running slower. So either way you analyze it, you come to the conclusion that if you have this acceleration involved, again, velocity is much less than the speed of light, no special relativity involved here, but just the fact that you have even a small acceleration, you'll find that the lower clock runs slower compared to the upper clock when they compare clocks. The lower clock sees the upper clock running faster, the upper clock sees the lower clock running slower in this case. And then you say, we've got the equivalence principle. Therefore, this situation also applies to a gravitational field. And you've got the acceleration going upwards, so if you put somebody in here standing in the elevator, if you make this equal to the acceleration due to gravity on Earth, then that person would feel a gravitational field. It would be like as a gravitational field, and Einstein would say, according to the equivalence principle, it's the same analysis either way. So the conclusion here is we did the analysis with an accelerated frame of reference and concluded that the upper clock runs a little faster than the lower clock, or the lower clock runs a little slower. In other words, lower down in a gravitational field, clocks are going to run slower than up high. Lower altitude, at a lower altitude in a gravitational field, like at the surface of the Earth, if one clock is at the surface of the Earth and one clock is up on an airliner or up in space on a satellite, this clock on the surface is going to run slower than the clock on the upper part, the higher altitude. And so this is gravitational time dilation. Is what we're talking about here. So not only do we have a time dilation effect at high velocities, special theory of relativity, when we're just in a gravitational field, there's a time dilation effect between lower clock and a clock higher up in the gravitational field. And they've actually done experiments with this. The physics building, they just sort of, from the basement to the top floor, they have two very accurate clocks, it's not quite set up like this with the pulses, but something similar to this. And you can actually see that the lower clock runs slower than the upper clock, even over just the height of a building. Again, if you have very accurate clocks involved. Another thing, we've actually mentioned this a couple times before, but the global positioning system, the GPS system, has to be designed to take this into account. And actually has to be designed to take into account the special theory of relativity and the general theory of relativity involving gravitation here. It turns out, if you do the analysis on the satellites that are involved in the global positioning system, they're moving at pretty high velocity compared to the Earth, and compared to just a reference point on the Earth. And therefore, it turns out if you do the analysis for the special theory of relativity, so special theory says that the clocks, since they're going faster, time dilation, right? If you observe the clock of a moving object that's going fast, you, the observer, say here on the surface of the Earth, and we watch the satellite going by overhead, or really the satellite might be stationary, but we're rotating on the Earth, however you want to look at it. We're at rest, satellite is moving, therefore we observe the satellite clock running more slowly, and it's about 7 microseconds slow per day is the effect. This is abbreviation for microsecond, millionths of a second. 7 millionths of a second slow per day. Gravitational time dilation, however, so the general theory of relativity, the general theory from gravitational time dilation, if you do the analysis there, remember the lower clock is going to run slower. The higher clock, in this case the satellite up there in space, is going to run faster. And so the satellite clock, from our perspective, runs about 43 microseconds fast per day. So there's sort of competing effects there. And you put them together and you can see that it's roughly, what is it here? 36 microseconds, something like that. It's in that range if I got the numbers quite right there. But 36, 37 microseconds when you do the analysis. Fast per day. And you might say, well, that's not a very big difference. If you're talking about millionths of a second, 38, 40 millionths of a second, whatever it is. But at the speed of light, as the signals go from the ground to the satellites, at the speed of light, speed of light in about 30 to 40 microseconds travels 10 or 11 kilometers. Right? What that means is, in designing the GPS system, if you don't take into account the special theory contribution and then the general theory contribution in the other direction, fast for the general theory, time dilation, gravitational time dilation, and slowing down for the special theory of relativity. If you don't take both of those into account and get the numbers right there, your GPS system is going to drift by 10 or 11 kilometers per day. In other words, it's not going to be a very accurate system. So they actually had to design the system such that the clocks ran slow on the satellites. Okay? In other words, they had to run slow by 36, 37 microseconds, something like that, per day compared to a clock, if an identical clock at the ground there. And so by taking that into account, they were able to get a very accurate system. So again, that's Einstein's happiest thought, or most fortunate thought of his life, depending on how you do the translation of the German. Occurred in 1907, developed it over the next several years into the general theory of relativity, or one key part of the general theory of relativity. And one of the consequences of that, again, is gravitational time dilation, that a clock in a gravitational field, lower down in a gravitational field, runs slower than a clock higher up in a gravitational field.